So in the second scenario here, what we want to do is we don't want to change the potential energy. So we leave it H2O liquid and H2O liquid. And so delta PE is 0. And that means any energy change is just kinetic energy. And so here the delta PE is 0. And so we'll be setting up all our problems like this. All our problems will either be at constant kinetic energy, that is, the kinetic energy doesn't change, or the potential energy doesn't change. Okay, one of these two scenarios. Well, we don't, you can do this, you can mix it. You can mix it where both the kinetic energy and the potential energy change, but even if you mix it, you have to take the two separate equations and then add them together. Like step 1, you change the potential energy, step 2, you change the kinetic energy. And so you get a Q1 term plus Q2 term plus Q3. You've probably done it before in a heating and cooling curve. In a heating cooling curve like water, let's go with ice. H2O solid. Let's say this is at minus 30 degrees C. And so this is a heating cooling curve. We change the kinetic energy. Potential energy stays the same. And so all the heat goes into, this would be temperature here. All the heat, this would be Q here on the x-axis. All the heat goes into warming it up. And then once we hit 0 degrees C, then all the heat goes into melting it. And so here, potential energy is constant. Here, kinetic energy is constant. And then once all of it's melted, then we warm up the liquid water. And once the liquid water has been warmed up to 100 degrees C, then we use that energy to boil it. And so we could separate it, or well, actually it's best to separate it. And so we have Q1. Q1, over here, Q is going to equal the amount times what? If we're warming up an object, what do we need to know about that object? We need the amount times, or a lot of people remember this as MC delta T, or the amount times C. C is called what? Specific heat or heat capacity. I use amount here because we don't always use the specific heat. Specific heat has specific units. What are the units of specific heat? Yeah, grams. Grams per calorie or joule per degree C. It's grams, it's mass. We could use the molar heat capacity, which would be grams per mole per degree C, or we could use some other. The heat capacity of an object. So for example, if you're building a concrete wall, do you want to measure how many grams your concrete wall weighs? Maybe not, or actually that's probably not the best. Let's say we're building a brick wall. You want to figure out the heat capacity of a brick wall. Do you want to weigh each brick and figure out how many grams each brick weighs? No. What you want to do is you want the heat capacity for the whole brick. What's the average heat capacity for a brick? And so we could have joules per degree C. Joules per degree C would be the object. You've seen that before in calorimeters. How many calorimeters do you use? One. Do you ever weigh it? Do you ever figure out how many grams of calorimeter you have? Like, for example, the styrofoam cups. You have 2 styrofoam cups, 2 lids, thermometer, whatever. Do you ever weigh that? No. And so that would just be joules per calorimeter per degree C. Okay, so we have many different units for specific heat, we don't have many units for specific, we only have 1 unit for specific heat. And so I don't like to use specific heat, I just like to use heat capacity. Therefore, I don't always write the mass here. It could be 1 calorimeter times the heat capacity of the calorimeter times delta T, or 1 brick times delta T here. And so, what we do is even if we have where the potential energy and the kinetic energy change in the same problem, we treat it as 2 separate problems and do 2 separate calculations and then combine the energies. Energies are added in. But anyway, normally when we're thinking about energies, we think in either changes in potential energy or changes in kinetic energy here. Change in potential energy would be a reaction process. Change in kinetic energy would be warming and cooling objects here. All right, so that's just brief there. And so what are we doing? We're looking at chapter 13 now. We were talking about entropy. And so I told you absolute entropy is unlike absolute enthalpies and absolute internal energies can be determined. So normally when we calculate the delta S, we just need the entropy of the final and the entropy of the initial. And so how are these determined? How are absolute entropies determined? And well, one way to determine them is by calculation. So this is Boltzmann. The Boltzmann. We can go down to the Boltzmann equation. Boltzmann equation is very simple. Let's take a look at the Boltzmann equation. Boltzmann equation looks at how many ways you can arrange the system positionally, or in terms of states. And the number of ways you can arrange that, the more ways there are, the higher the entropy. The fewer ways there are, the lower the entropy. And so this is just going through, we'll call microstates here, and just numbering how many different microstates there are. And then once we know how many ways there are, then we can plug it into the Boltzmann equation for entropy. This is the Boltzmann equation for entropy here. And so we could do it by calculation. And the entropy, the absolute entropy, this is not delta S, this is just S. S is equal to K. K is called the Boltzmann constant. And so that's what the little b there means. It's just Boltzmann. In fact, this equation's engraved engraved on his tombstone. S is equal to K log W. And so K log W. W is the number of ways or microstates, or ways that you can arrange it. So for example, in a perfect crystal at 0 Kelvin, how many ways are there to arrange the atoms in a perfect crystal? How many different ways can you arrange the atoms in a perfect crystal? There's actually only one way. Everything has to be perfectly arranged. And so it's very constrained there. If there's only one way to arrange the atoms in a perfect crystal, then W equals 1. And the log of 1 is equal to, log base 10 of 1 is equal to 0. And therefore the entropy is 0. So the absolute entropy of a perfect crystal, in which there's only one way, is 0. And that's the most constrained, because everything has to be perfectly arranged. Now what happens if you warm up the crystal? If you warm up the crystal, then the atoms start to vibrate, so there are more positions that the atoms can adopt. And so more positions, you figure out how many microstates or how many different positions you can have, and then you could figure out the number of ways to arrange it. And so we aren't actually going to do any of these, but you could do this, statistically by looking at microstates, as shown here. These are for energy in this case. If we look at this, this looks like energy. In fact, if you look at these numbers here, we see quantized energy levels in the population. Population of these species in those quantized energy levels. That's what we're saying. We typically end up with like a Boltzmann style distribution depending on the temperature, because when we look at the population of energy states, at a given temperature, let's say we have T, temperature equals T. Well, we'll just go RT here. And we look at the population and graph that. And so this would be the population here. And this would be the energy, because what we're going to do is we're going to tilt that on its side. If we tilt that distribution on its side, then you're going to look at a distribution that looks like this. This is called the Boltzmann thermal distribution. That is, at a given temperature, we're going to have the highest population at some energy, we'll call it here, and then these lower energy states are going to be less populated, and these higher energy states are going to be less populated. but the bulk of them is going to depend on the temperature. Now, if we increase the temperature, what's going to happen to the population, or the population of these states? If we increase the temperature, then that should shift the population to higher energies. Of course, would be what we call the ground state here, very low energy. This would be like 0 Kelvin, something like this. But there's still probably vibrations. And so as we increase the temperature, we can change this distribution. So at higher temperatures, the distribution flattens out a bit, but you can see the higher energy states are going to become more populated here. So we tilt that on its side, just look at the population here. At lower temperatures, what's going to happen? At lower temperatures, we'll populate the lower energy states more, like this. So this would be a lower temperature. This would be a higher temperature. You've seen this distribution before. What chapter did you see this distribution? You recognize this distribution?
Gas velocity?
Yeah, gas velocity. Do you remember that? And velocity is related to kinetic energy. Right? Velocity and kinetic energy are related by Newton's law in physics. And so rather than using velocity, we can just plot this as energy. It's going to adopt the same curve. And so this would be the energy. So this is called Boltzmann distribution, Boltzmann thermal distribution. But basically, it's this. And so we look at, a number of ways to arrange things. Well, anyway, we're going to continue on here because we aren't going to do this. We aren't going to figure out the number of ways. Like the red could be up here, orange could be up here, yellow could be up here, green. And these are just color coded to differentiate it. Otherwise we call it, 1, 2, 3, 4, 5, and 1 could be up, 2 could be up, etc. And so there's 5 ways of arranging this with this population distribution, etc. And so this is just counting. People. Well, if you have an Avogadro's number of molecules, is that something you want to do? Is count them one by one? No. And so, this is just talking about. You know what K is? K is just R over NA. It's the gas law constant. This is for the thermodynamic gas law, 8.3145 joules per Kelvin mole over Avogadro's number. So it's R, not for mole, but for atom, per article. I'm going to skip some of these. And so there's one way of figuring out the number of microstates here. Here you can see there's a lot of ways here. 10 to the 10 to the 23rd power. Huge number. But what we're going to look at is, I kind of skip all this stuff. Just more about the microstates. Maybe I shouldn't skip this. This is a new edition. You can see there's a lot of discussion about this. All right, so when you calculate it, like this. By figuring out, number of ways. The more ways, the higher the entropy. The more ways, the less constrained. The fewer the ways, the more constrained. But entropies can be experimentally determined too. And so this calculation, let's talk about experimental determination of entropy. The experimental determination is, the change in entropy is related to, entropy is related to the heat. You know, how much it's actually, let me just write the equation here. This is the integral from calculus. This, you don't have to do anything with this equation here. And then d, this is a very small delta, you know, infinitesimally small delta. Very, very small delta. We'll just give it a d. dq. dq reversible. You know, we do this heat transfer very slow at a given temperature of T. dq reversible, this is going to be related to the heat capacity. And so we can relate to heat capacity. And basically what this equation just tells us is that entropy, absolute entropy can be determined. How do we determine absolute entropy? Because this is delta S. Well, the way we do absolute entropies is we do S final minus S initial is going to equal this. And what we do here is we solve for S final, but we need some kind of S initial. S initial is going to come from the third law of thermodynamics. From the third law of thermodynamics, we say that if we start off at 0 Kelvin for the perfect crystal, the entropy should be 0. And so from the third law, we'll just start off at 0 Kelvin. And the entropy is going to be 0 at 0 Kelvin. And so essentially what you have to do is the integral, what this is this is just pretty much the area under the heat capacity curve. And so let's take a look at the water as an example, H2O liquid. And you measure the heat capacity at various temperatures. And so do you know what the heat capacity of water is at 4.18? Yeah. Does it change? Does the heat capacity change? So is it pretty much constant for water from 0 degrees C to 100 degrees C? Or does it change a little bit?
Changes in different states.
It changes with different states for sure, but does it change within a state at different temperatures? No? Or it doesn't change much. It depends on how many sig figs you have. You know, if we use 4.18, then it's pretty close. But if we start to try to be more precise, then we're going to see it does change with temperature. In fact, for water, you know what an empirical equation is? What's an empirical equation? I mentioned it before. Well, anyway, it does change a little bit, you know. And so, for example, if we look at this is the heat capacity as a function of temperature here at constant pressure. And delta H or dH, H is equal to delta H is equal to delta U plus T delta V. And delta U is going to equal Q plus W plus P delta V. So it's going to be related to there. And so what's done here is this is more of a. There are two approaches we could do to this. One, you could do a more theoretical approach to this. Doing a more theoretical approach, we're using thermodynamics here to come up with an equation showing that the heat capacity does change with temperature. This is the heat capacity of nitrogen gas. And you can see here, it's has a weird dependence on temperature here. And so as the temperature changes, so does the heat capacity a little bit. This is from chapter 7, by the way. And for water, this is it. How much heat is required to convert 10.0 grams of ice at -5 degrees C to steam at 100 degrees C? The temperature-dependent, constant pressure, specific heat capacity of ice is this. Even ice shows an interesting temperature dependence here on the specific heat. Normally, people take ice specific heat to be 2.01, 2.01 joules per gram degree C, something like that, right? But it changes a little bit. And so if you want to do a more accurate calculation, we have to take into account the slight change in heat capacity. The temperature-dependent constant pressure, specific heat for water it's not 4.18. The specific heat of water as a function of temperature is equal to -1.0 times 10 to the minus 7 temperature cubed. This is third order equation, plus 1.0 times 10 to the minus 4 temperature squared minus 3.92 times 10 to the minus 2 T plus 8 point. Where the heck did this equation come from? Typically where this equation comes from is they measure the slight variations in heat capacity with the temperature, and then they try to fit that dependence with a mathematical equation. This is a mathematical equation. Come up with this, an empirical equation. Empirical equation usually comes from observation rather than a theoretical approach to doing it. And so it depends on how accurate and how precise you want your answers to be. Do you use 4.18, or do you go for it and try to be a little more accurate with this to calculate better specific heat? And so with water, what you do to get the entropy, the absolute entropy is this. You measure the heat capacity of water at various temperatures. So let's say the heat capacity here is measured here, or specific heat or whatever. So you measure CP at different temperatures here. And then this would be steam, and then liquid water would have a higher. Why does liquid water have a higher heat capacity or specific heat? Things with a high heat capacity mean what? Things with a high heat capacity means they.
Strong intermolecular forces.
Well, they could have strong molecular interforces. They could have lots of ways to vibrate. Lots of ways to rotate. There are lots of ways to absorb heat. For example, water. When you add heat to water, water is what they call a heat sink. It's a heat sink that has a high heat capacity. There's a lot of ways to absorb heat or energy and to do different things in water. Whereas if you heat copper, if you heat a copper pan or something like that, are there a lot of ways? Does copper have a high heat capacity, or does copper have a low heat capacity? Low heat capacity. All copper can do is vibrate, back and forth. But water has a lot of ways to take in that heat. And so water has a pretty high heat capacity. Then you go back down to ice. Ice is going to have a lower heat capacity. So you can measure these. You can measure these very close to. Actually, I didn't do this right. But you can measure these very close to. You can almost get down to 0 Kelvin. Can't get down to 0 Kelvin though. You can get very close. Like liquid helium. Liquid helium is very common. And do you know how cold liquid helium is? Liquid helium, you can buy this stuff. Well, there was a shortage of helium for a while, but now I think it's okay. But you can buy liquid helium. I used to have to use liquid helium. Liquid helium. I use these magnets, these gigantic superconducting magnets, and they had to be cooled down to liquid helium. Actually, they didn't have to go that cold, but we cooled them down to liquid helium temperature. The liquid helium blows away pretty fast. And so they used to have to fill the tank with liquid helium once a week. I think it was, yeah, once a week. And then liquid nitrogen every day, because you had liquid helium in the core and then liquid nitrogen around that to cool, provide some kind of thermal barrier. Liquid nitrogen can boil off pretty rapidly every day. Helium, I didn't fill. We called somebody to come in to fill that. Helium, you know what the temperature of liquid helium is? 4 Kelvin. 4 Kelvin. And so you can cool things down to 4 Kelvin pretty easily using liquid helium. And so you take these measurements, but are we going to get a measurement? What is the specific heat at 0 Kelvin? It doesn't make any sense because at 0 Kelvin, is there any way to absorb energy at 0 Kelvin? Not unless you warm it up, right? If you warm it up, then it starts to vibrate, but there's no vibrations. And so with the third law, what you can do is you can just extrapolate this. We back extrapolate this to 0 using the third law. And so there's no data here. And then we have data here. And there's going to be a jump up. So this is a specific heat or heat fasting versus temperature for H2O. This is H2O liquid here. This would be H2O gas here. Or this would be H2O solid here. Okay. And then what you do with this integral sign here, this one, we do with this one is we just take the area into the curve. So we measure the area. So if I want the entropy of H2O solid at this temperature here, I'll just go figure out up to that temperature is the area. This would be the entropy at this temperature, and that would be the absolute entropy at that temperature.
Will they ever actually give you the function of the curve, or do you just manually find it?
Empirical equations, there are two ways to get the function of the curve. One is you just use a Excel or some other software package to do a fit. And so what you do is you pick an equation and you try to fit it. The problem is you can pretty much fit a lot of different data with a high enough order equation. And so if you start getting into like t to the 6th, and so a t to the 6th plus b t to the 5th plus c t to the 4th, it starts to become meaningless, because you just add more and you go to higher and higher order equations, but physically it becomes meaningless because, it's not an actual fit. And so this happens in science. In science, let's say I had something that's supposed to be linear. It's supposed to be linear, but because of there are two types of error that we worry about. What are the two types of error that we worry about? This is from chapter 1, chapter 2. The two types of error we worry about. Systematic and random error. Typically, this is fluctuations due to random error here. Random error. But if you have a 6th order equation, you could hit every dot right on the button. It just, it fluctuates like this. You could eventually you'll have some weird function like this that can kind of curve up. But is it meaningful? In terms of the physics? No. What happens is we just got random error. Really, what we should have done is fit this. This is let's say it's supposed to be linear, something like that. And you see some points are above, some points are below. And so, yes, you can fit, the data to some mathematical equation, but we have to be careful. That's an empirical equation, and what we want to do is we want to make sure we can relate it to something like theoretical. And so, what a lot of people do is they measure like cooling curves. Like in calorimetry, you measure something cooling. When you measure something cooling, does it do something like this at times? I'm measuring cooling curve, and there's one data that pops up. And so we can fit this to some funky mathematical equation that goes like this. And so you have a hot cup of coffee, And so what you say is, okay, I had my hot cup of coffee, and all of a sudden it warmed up, and then it cooled down, and then warmed up again, and then cooled down. Is that how a hot cup of coffee cools down back down to room temperature? You know, it fluctuates. You know, sometimes it'll warm up, sometimes it cools down, sometimes it warms up. Is that how it does it? No. And so, yeah, we could fit it, but we want it, when we fit these things, we'd like to fit it to some kind of, you know, no, it cools down smoothly. These warm-ups are just random fluctuations in the data. They aren't necessarily real in the sense that it's actually warming up, you know. And so there are two ways we can derive it. One way is empirically, the other way is theoretically. We have a two-pronged approach in science always, you know. We do things by observation and we do things by theory. You know, the best is to do, you know, both. And so, yeah, I'm sure people have tried to come to calculate these theoretically. In fact, that's what this first one, this is what I was trying to show earlier. What I was trying to show earlier is, this is the more theoretical approach. They want to figure out how the specific heat changes in temperature. Okay, and so they're looking at the thermodynamics of this. And so this is what all this is about. And then they come up with a function to do this. Actually, here, somewhere here, right? But then they say, on the other hand, okay, so this is more kind of a theoretical or calculative approach to it. On the other hand, you often find that the heat capacity is a function of temperature, a convenient empirical, actually this is not theoretical, I should read this more carefully. A convenient empirical expression. Well, what the heck is empirical? Empirical is so common in science. Everybody in science should know what empirical means. We use it all the time because we're always thinking about relationships, how things change with this or how things change with that. And so we have that two-pronged approach. We got the empirical, and we have more than a two-pronged approach, because the purely theoretical calculations, they give another name for, like you might hear ab initio, you know. Then there are other approaches, you know, like if you do like ab initio, that's straight from theory, you know. You don't care about the experimental data, you're just trying to figure it out using computer and quantum mechanics. And then you have the empirical approach. The empirical approach, the brute force empirical approach is you don't care about, you know, the theory, you just try to fit this. What we do oftentimes is a semi-empirical approach. A semi-empirical approach is trying to mix, you know, the two. You know, full ab initio can be subject to errors in the calculation or just difficult. You know? And a purely empirical approach, you don't want to ignore the theory. You know, this should be cooling, according to Newton's law of cooling, should be cooling a smooth cooling curve. So we do semi-empirical. Semi-empirical takes some empirical data and mixes it in with a theoretical calculation. Those types of things you should know. So this is back in chapter 7 here. When we're talking about empirical equations. I forgot where it came up. And so actually, I didn't know. This is an empirical equation. This equation just comes from, it looks like it fits this curve. You know? What's the theory underlying this? You know, why is there square dependence here? Or, you know, that's for nitrogen gas. If we go here, you know, this is for liquid water. Why is this third order here for water, liquid water, and it's second order for nitrogen gas? And where do these coefficients come from? Those coefficients, these are empirical fitting coefficients. This isn't the first empirical equation you dealt with. The first major empirical equation you dealt with is back in chapter 6. Let me show it to you. Do you guys remember what it's called? The first major empirical equation? Well, actually, it's not. It might not be the first, but the ideal gas law. It's an empirical equation. Where did that come from? Did that come from theory? No. It just came from fitting the observation. And also in chapter 6, there's another big one, a big empirical equation that came out of chapter 6, which is called the van der Waals equation. Now, the van der Waals equation, you know, how the heck did somebody come up with this equation? Did they come up with this equation from theory? No. All they did was they tried to fit the curve. They say, hey, it's not linear. Tried to fit the curve. They tried to, well, it depends on what you're looking at. And so they fit the curve, and then they come up with these constants, A and B, you know, the van der Waals constants. Where did those constants come from? Did that come from theory? No, that came from fitting the curve. You know, with this equation, when you fit the curve with this equation, you get A. That's how you got the slope. When you try to fit this line, you know, we get M, the slope, from the fit. Well, it's the same thing with A and B. We just fit it. And so the van der Waals equation is another big empirical equation that came out. There are a whole bunch of equations that deal with real gases versus ideal gases. Van der Waals is just one of them. Another equation that somebody came up with is called the Virial equation. And there are, I think, several other equations to try to do a better job of fitting the behavior of a real gas versus an ideal gas. Okay? You can also come up with these theoretically as well. You know, the best is to be able to do both. You know, the best is to be able to derive. You know, for example, you know about quantum physics versus classical physics, right? You know, quantum physics doesn't have the same equations. But did you know that you can derive all of Newton's laws of classical physics from quantum physics, theoretically? And so all those. Newton's laws are empirical as well, you know, dropping the apple or whatever else. I remember doing that in physics, dropping masses and taking measurements and then coming up with the equation that describes that. But anyway, going back to this, yeah, these are just done experimentally. And of course there's going to be random error, and so you just try to smooth that out and come up with a good fit. And so we get this, and then if we want the absolute entropy at this temperature, that would be it. If we want the absolute entropy at this temperature, we'd have to determine the area from 0 Kelvin all the way up to T. And then we get the entropy at temperature T here. And so H2O gas has a higher entropy because we've got to take all this area plus this, and then we get the entropy at this temperature here. And so from this, we could get the entropy of water at any temperature. Well, that's a lot of data just for water. What do you think, you know, what, if you're going to pick one temperature and you want to know the entropy of water at one temperature, what temperature would that be? Would you say 0 degrees C would be the most convenient temperature to know what the entropy of water is? 0 degrees C? No, that's not a very convenient temperature. What do you think the most convenient, the most useful temperature to know the entropy? Room temperature. Room temperature would be what temperature? 25 degrees C. So what we're most interested in is what is the temperature, or not the temperature, what is the entropy of water at 25 degrees C? Well, the entropy of water at 25 degrees C is just this, whatever this is here. And that's the entropy we want to know. And so what is that entropy? Well, let's look it up. Then, you know, we want to know the entropy of a lot of objects at 25 degrees C, and we're going to compile these into a table. Where do you think the most convenient place to compile these is? The most convenient place to compile this is in Appendix D. Right? In Appendix D, we're going to have the entropies here. And so let's take a look at the entropies here. You see, when we look at the absolute entropy, I mean, what does that superscript 0 mean? Standard. Standard. Take a look. This is delta. This is a change. This is delta. This is G we're going to talk about in this chapter. This is S. What's CP? Is that the specific heat? Now, this is not the specific heat, because the specific heat would be joules per gram. This is joules per mole. That would be called the molar heat capacity, or just heat capacity. We could use heat capacity for anything, for specific heat or whatever. In fact, it's probably better. That way you don't pigeonhole yourself or fix yourself into only using specific heat. But anyway, we're going to ignore this. We're just looking at this here. Anyway, the higher the heat capacity, the more ways there are to absorb that heat, right? And typically we'd expect a higher entropy with a higher heat capacity. But let's just look at the entropies themselves. Now, the entropies are in terms of joules. This is joules per mole Kelvin. And so the entropy here is going to depend on the number of moles, and it's also going to depend on the temperature. But the temperature here is fixed. What's the temperature in appendix D? You know, we don't have all the temperatures because it would just be way too much data. It'd probably be better to express this as a mathematical equation. That way we don't have to write the individual numbers for everything. We'll just have an equation you can plug everything into, figure out what the entropy is. But we don't have that. We're just going to put in the most convenient temperature. The most convenient temperature is 25 degrees C or 298 Kelvin. And so here, these are the entropies at 298 Kelvin. So we can do the same thing for aluminum. If you look at aluminum solid, the entropy is 28.33. Is that low or is that high? And so what you have to do is you have to look, you know, what is the lowest entropy in the table? What is the highest entropy in the table? And so if I look, let's take a look at the first page. And I look for the lowest entropy, and I see the lowest entropy. The lowest entropy is minus 321.7 joules per mole Kelvin. Minus 321.7 joules per mole Kelvin. A lot of people, they don't care about numbers. Numbers are totally meaningless. You know, they just understand things like conceptually, but they don't want to deal with the numbers. But do you have a problem with minus 321.7? Does that sound like a good? Maybe that's not the lowest. Let's see if there's a lower entropy than minus 321.7. So minus 73.2, minus 53.1, minus 56.9. Minus 99.6. Minus 315.9. Minus 315.9. And 3. Minus 222. A lot of people, they never look at a table, surprisingly. Never look at the entries in a table. But if you do, you're a step ahead. It doesn't take much work. Well, I think that was the lowest because now we're at the end of the table. So let's go back to the beginning of the table here. Minus 321.7 looks like it's the lowest. Is there something weird about that? Well, the answer is there is something weird about that. You know, because a perfect crystal has an entropy of 0. And so is there something like better than a perfect crystal? Like a perfect exceptional specimen
A single atom.
of a crystal? A single atom? This is not a single atom because this is per mole. This is per 6.022 times 10 to the 23rd atoms. That's the entropy for a mole of atoms. So what would you call something better than a perfect crystal? Something more ordered than a perfect crystal? But you already know, right? You guys already know there's a trick to table D. What is the trick to table D? Kelly, you remember the trick to table D? No? Okay. Paul? Don't remember? Table D's tricky. Well, a lot of people say table D's easy, you just look up the values. But this isn't the first weird entry you've seen. What was the first weird entry you've seen? Kelly, you remember the first weird entry? No? The first weird entry you saw was for delta H as a formation. It's right here. Do you see it? Where's the weird entry in delta H as a formation? An entry that doesn't make sense.
Copper liquid.
No. Copper.
It's copper solid.
Copper solid's okay. You know, the enthalpy of formation of an element in its normal state under these conditions is always 0. My battery's about to die. Why is my battery about to die?
Hydronium ion?
Hmm?
Hydronium
Yes.
has the formation of 0.
Has a formation of 0. That's odd. Somebody explain to me why. This to form H plus aqueous, you guys remember formation reactions, right? To form H plus aqueous requires this. We form it from the elements, so it would be hydrogen gas. We need half a mole. And so this is a half a mole of hydrogen gas going to H plus aqueous. Delta H for this reaction is equal to 0 kilojoules. So if I want to form a mole of H plus ions, hydronium ions, or hydrogen ions, it costs me 0 kilojoules. Is that right? That's totally wrong because I have to break a half a mole's worth of hydrogen-hydrogen bonds. Hydrogen-hydrogen bonds, that's going to cost me how many kilojoules per mole, roughly? Just take a guess. How many kilojoules per mole does it take to break a hydrogen-hydrogen bond, a single bond? Ballpark.
400.
Yeah, about 400. So it's going to cost me 400. How much energy is it going to cost to ionize that H plus? You guys, what should be the hardest element to ionize?
Helium.
Helium. Helium's like 2,000 plus kilojoules per mole to ionize, and then hydrogen's lower than that. So like over 1,000 kilojoules per mole, right? And so far, we're in the hole for about 1,400 kilojoules. We're in the hole for about $1,400. How are we going to break even? Well, we're going to break even by going AQ. Going AQ means we're going to form what? Well, when we go AQ, when we have an H plus or H3O plus AQ, what does that mean? I know it's going to be H3O plus. We always take it as H3O plus, but we'll just leave it as H plus for right now. Well, AQ means it's going to be, it's going to be surrounded by waters. When it's surrounded by waters, is it stabilized or destabilized? We talked about this before with lithium ion. What was special about lithium ion? Or we talked about it when we're dissolving sodium chloride. It's called hydration or solvation. When we hydrate ions, we form ion dipole attractions, which will help stabilize it. And so, are we going to get 1,400, let's say, kilojoules back, roughly, or between 1,000 and 2,000. You think we're going to hit that exactly? No. So something's very odd, and in fact, we probably aren't going to get that back. And so why the heck is this 0? Actually, it isn't 0. Now is it coming back? Is it coming back? And so what did we do? What did we do in Chem 1A? Well, I mean, why is it? Why do we have a 0 here? It shouldn't be 0. And so what did we do? You remember? Right. Kind of a reference point. You know, and this is the problem with with tables like this. With tables like this, they expect you to know this type of stuff. They expect you to have studied it. They don't expect you just to use it. You know, if you're just a user, anybody could do that. Use the table, plug it into the equation, do your calculation. Basically, that requires no skill and no knowledge. Right? To understand the table is different, though. To understand the table requires more in-depth knowledge. And so a lot of people know how to use Appendix D, but they don't really understand Appendix D at all. And they don't understand Appendix D consists of how many different tables all combined into one. In fact, this is arbitrarily defined. This is arbitrarily defined as 0. Well, what about delta H of formation of H2? Is that arbitrarily defined as 0? No, that is actually 0. Because if we form H2 gas from H2 gas, there's no change. And therefore, there's no change in energy. That is 0. This, however, is arbitrarily defined as 0. How come? Somebody explain to me why that is arbitrarily defined, why you need to arbitrarily define that as 0. Let's stop picking on Kelly, but Paul, how about Paul? I'll pick on you. Yeah. Okay, that's fine. Kelly, you remember? It's easy to forget. I mean, it's easy to forget because you know what a lot of people do is they just try to remember what I say, but you don't want to remember what I say. What you want to do is you want to put it in your own words. You know, because if you put it in your own words, you know, it makes it much more valuable and it makes it much more memorable. And so rather than trying to remember what I said, is you put it in your own words, and then what you do is and this is why it's so important. When I was a student, I would always annotate my notes. So I'd have some stuff I'd written what the professor said, and next to it, I wrote down, well, this is what it means to me. And then I'd verify it. You know, am I understanding this correctly or not? You know? Because I want to explain things in my own words, and that way when I read, you know, I just read my notes before the test. You know, for the final exam, once I started doing that, I didn't really have to study for the final because I reread my notes regularly. And I remember what it said because everything is from, actually, Megan, do you remember? There's one more person I could put down. Why we have to arbitrarily define this as 0? No? Okay. Well, nobody remembers. And so, since nobody remembers, I'm thinking, well, I have two choices. One, I could just tell you, but if I tell you, it's so easy to forget. Or two, I can have you figure it out. If you figure it out and you have to actually figure it out yourself, then maybe that's better. And so why don't you guys figure it out yourself rather than me telling you that, you know, there are actually 3 tables incorporated into here. And the equivalent thinking would be you can't compare all the numbers. So, so for example, in delta H of formation, I look at this, minus 1.7, and I try to compare it to 0. Hey, that's close to 0. Is that accurate? This minus 1.7 is close to 0. Is that accurate? No, that's totally inaccurate because you cannot compare these two numbers. Comparing these two numbers is like comparing, hey, what's the biggest apple? Well, here's the biggest orange. I got the biggest orange for you. Well, I didn't ask about oranges, I asked about the apple. Well, that's what these is. This is apples and oranges here because these two numbers don't belong in the same, they should be in different bins. Well, why didn't they put it in 3 separate bins? They didn't put it in 3 separate bins because it take up too much space, and by this level, you're supposed to be more sophisticated to be able to deal with this kind of complexity, I think. But you know, I get tired of repeating this semester after semester, and so I wish they would have put 3 separate tables. It would be great if they made 3 separate tables. Then I would spend a lot less time. You know, I don't know. I spent like 3 days in Chem 1A going over this repeatedly. You know, 3 times. I'm going to repeat it 3 times at least in Chem 1A. And then I do the same in Chem 1B, but I do it fewer times because we don't have enough time to go through it. But basically, you can't compare. I can compare this number and this number. These two are no problem. But basically, the cations, you can compare cations with cations, but you can't compare cations with anions. You compare anions with anions, cations with cations. And then you can compare neutrals with any other neutral species. And that works. Okay. And so the way I visualize a table like this, in my own thinking, this is the way I came up with it. This is like having Kelvin, Celsius, and Fahrenheit temperatures the same. And so I could say this. Oh, yeah. Minus 1.7 degrees Fahrenheit is very close to 0 Kelvin. Right? Minus 1.7 degrees Fahrenheit is very close to 0 Kelvin. They're about the same. Minus 1.70, pretty close, you know, when you look at all these numbers. Right? No. Wrong. Wrong. Hey, minus 32 degrees is very close to minus 31 degrees, right? Minus 32 degrees is very close to minus 31 degrees, right? Yeah, if they're both Celsius or they're both Fahrenheit, yeah, they're pretty close. But if I said minus 32 degrees C is very close to minus 31 degrees Fahrenheit, is that right? No. And that's a problem because all these are kilojoules per mole. And so they all have the same unit, but they're all referenced, and Kelly has this right, they're all referenced to a different 0 point. And so go back to chapter 7 and look it up. It's in chapter 7. Well, that's the reason why you see this. Hey, minus 321.7 Fahrenheit is way lower temperature than plus 28.33 Kelvin, right? Minus 321.7 Fahrenheit is way lower temperature than 28.33 Kelvin, right?
No.
So which number is lower? Which one has a lower entropy? Aluminum 3 plus or solid aluminum metal? Hey, most people will say solid aluminum metal has a higher entropy. Aluminum 3 plus has lower entropy. Most people say, not most. In Chem 1A, I asked this question on the test. Maybe I asked this question on your guys' test. Is minus 321.7 joules per mole Kelvin lower? I mean, in the absolute sense, or I shouldn't say, because energy is very tricky. But is this, you know, is we're talking about temperature, maybe that's a little easier to understand. Is minus 321.7 lower than 28.33?
terms of temperature?
In terms of temperature, yes, right? In terms of temperature, yes. In terms of using this table, no, because we can compare neutrals with neutrals, cations with cations, anions with anions, but we cannot compare cations with anions or neutrals. And so these numbers don't compare. They're a different scale. Why are they different scale? Because they have a different reference point for zero. That's it. And so you'll see this reference point again for entropy here, and this is the reason. You can go back to chapter 7 and look it up because maybe that's more effective. I have a feeling if I talk about it again, it's not significant. It's just blah, blah, blah. It's blah, blah, blah until somebody asks you this, and then you don't know the answer. You know? And it's such a common table. But take a look at this. A, B, C, D, E, F, G, H, I. The absolute entropy of H plus, 1 molar H plus, 1 molar H plus at 25 degrees C is 0. Is that true? What does you know, according to Boltzmann's law, what does the entropy of 0 mean?
0 Kelvin.
Well, it would have to be 0 Kelvin because we don't want any movement, right? If there's movement, then there are more microstates, more waves. And so, according to Boltzmann's law, W has to equal a perfect crystal. W, the number of ways to arrange the atoms is not 0. There's just one way. There's only one way. And so, if H plus, 1 molar H plus at 25 degrees C has an absolute entropy of 0, what does that mean? That means there's only one way to arrange. So the water will perfectly arrange it like this. The hydrogen will perfectly arrange like this. And the water over here, it's got to be perfect. It can't be off a little bit. It has to be perfectly arranged. Does that make any sense? If you have liquid water, you know, we can't have any movement. Everybody has to stay in their place, and nobody can move. Is that physically realistic? No, this is an impossible number. Well, it's an impossible number because it's not a real number. The absolute entropy is much higher than 0. And so why did they call it 0? Well, that's what you can do. You can go back in chapter 7 and look it up. Why this is the case. Why do they have to do this? In fact, the heat capacity. What's the specific heat of 1 molar H plus? The specific heat of 1 molar H plus is 0. It takes 0 joules. 0 joules to warm up a mole of H plus ions by degree C or Kelvin. It doesn't make sense. Well, maybe it's a typo. Is it a typo? It's got to be a typo. You know, because the lowest entropy possible is 0. And I've already saw an entropy of minus 321. What's the lowest Kelvin temperature possible? 0. Can you have minus 321 Kelvin? No. Okay. All right, and so the same thing here with entropies. You've got to worry about it. And I'll ask you again. You can go back and look at chapter 7. But the same thing with entropies. We can compare neutrals with neutrals, cations with cations, but anions with anions, but we don't want to cross-compare. And you see that. And so that was a cation, aluminum 3 plus. We don't compare these two numbers. 28 and 33, 28, 33 and this one aren't in the same category. But we can compare this. You know, and when we compare this, aluminum looks 2833, so It's pretty low. Let's see if there's something lower that's neutral. And so we go on and we see, you know what, the lowest entropy is, come up here. Look at this, carbon, diamond, 2.38. It's a very low entropy. And then I'm going to save some time here. When you scan the table, you'll see that entropies for solids range from about 0 to 100. It's a typical range for solids, 0 to 100 joules. The entropy for liquids is around 100 to 200. The entropy for gases is over 300 or over 200. You know, gases are over 200. Sorry, not 300. All right. There are some exceptions, of course. So, for example, if we know that range, then we see that there are some solids that have kind of a high entropy, you know, and there's some gases and or liquids that you can have. Like, for example, this gas has an unusually high entropy. This gas, Al2Cl6, has an entropy of 490. That's kind of high. But these look all okay until we get to this. What's unusual about this? Aluminum sulfate.
It's a solid.
Well, it's a solid, but when you look at the entropy, look at that entropy. You'd call that entropy high or low for a solid? That's kind of high. Well, why is it high? Well, why it's high, and it turns out, is the sulfates. These sulfates are tetrahedral, and they're spherical, and they can spin. You know, they're like little balls trapped in the crystal lattice, and they can spin like this, increasing the entropy quite a lot. They aren't locked, and so there's mobility in that sulfate, perhaps. You know, well, that kind of phenomena happens, and can increase the entropy. And then there's some entropies that, you know, those entropies are kind of high. You know, they're more disordered than you'd expect. But there's entropies that are kind of low. One of the entropies that's kind of low, we can see, is something like this. Look at that. You see an entropy that's kind of low? I mean, kind of lower than you might expect.
I guess.
Yeah. Some of these, like this one here, water liquid. Liquid water has a kind of a low entropy. You see that 69, 91. Why is that? It have a lower entropy than
Hydrogen bonds?
hydrogen bonds, strong hydrogen bonds in water. These aqueous solutions also have kind of low entropy because of the hydration spheres of the molecules. But and so you could just look and get a feeling for entropies. And so it turns out that once we have the numbers, and we don't have to do this, we aren't going to do any kind of calculation to derive these types of things, but calculating delta S is so simple. If we want to calculate delta S, we're going to do it under standard conditions because we want to use Appendix D. And so all we do is consult Appendix D. It's going to be nu P times S of the products minus nu R S of the reactants. So we just sum up the products minus the reactants, and we can determine the entropies. And so we can figure out the entropies without too much difficulty, as long as the temperature is at 25 degrees C, and as long as the species is on this chart. And so let's go ahead and do entropy calculation. So we know this. For example, combustion of methane, CH4 gas plus 2O2 gas yields CO2 gas plus 2H2O liquids. And so what's happening with the energy here? Is energy going up or down? Energy is going down, and so that's favorable. And we can calculate it. It depends on what conditions we do this under. If we do this under constant pressure conditions versus constant volume conditions, would I get a different amount of energy? Would I get a different amount of energy? If I did this under, in other words, if I burn a mole of methane in the open lab here versus burn a mole of methane in a bomb, would I get the same amount of heat? No. The answer is no. I'd get a different amount of heat, right? And so I have to figure out, do I want to do a delta H calculation or delta U? Delta U will tell me how much heat I'll get if I burn it in a bomb. And so I would just burn this in the open lab. So the delta H calculation is easy, right? For delta H, we just do the enthalpies of formation of the product. So we have 1 mole of CO2. We figure out what is the enthalpy of formation of CO2. Now, using the table is easy. We just look up the value here. And why can we, if this is 3 different, why can we use, 3 different values in the same equation? The reason we can use 3 different values in the same equation is because of systematic error. All the cations are systematically off. They're too low. All the anions are too high. And they're equal and opposite. So what happens is, can you form a cation without an anion? No. And so one systematic error drops it down, the other systematic error lifts it up, and they self-cancel. And so we can use the same values in a single equation. We don't have to have 3 equations. 1 equation for cations, 1 equation for neutrals, and 1 equation for anions. It's from chapter 7. And so let's go to CO2 first. And so the state matters. It's going to be CO2 gas. It's minus 393.5. I have 1 mole. So 1 mole of minus 393.5 just gives me 393.5 kilojoules. And then I have 2 moles of water. And so the 2 moles will cancel out. So this is going to be 2 times the delta H formation for liquid water. The delta H formation, water is going to be H. So let's go down to H here. H2O liquid. We go over here, minus 285.8. 285.8 kilojoules. Right, the moles cancel out. Okay, so that's the sum of the products minus the sum of the reactants. Methane. Methane is going to be on another table, the table of organics, which is at the end of this table here. And so let me go find the organics here. So we end up with zinc, and then we have methane here, the organic substances, minus 74.81. 1 mole minus 74.81 kilojoules is what it's going to give me. And then oxygen. What's the delta H of formation of oxygen, O2 gas? It's 0, so we don't have to look that up. And so when we calculate the delta H, this is called delta H of combustion because it's a combustion reaction. We can go ahead and do that here. So I'm going to get 2 times. I get 890 minus 890.29 kilojoules. And so that's an exothermic. Energy goes down. So it's good. And of course, this has to be at 25 degrees C. The reactants are at 25 degrees C. And the products must be at what temperature? The products have to be at 25 degrees C. And so this is why water is a liquid. Water is a liquid at 25 degrees C. Even though, initially it starts off as a gas, cools down, goes back to a liquid and releases more energy. Well, delta S is the exact kind of same calculation. Delta S is just as easy to calculate. And so let's go ahead and calculate our delta S. What do you think? Tell me what you think happens with entropy. Does entropy go up or entropy go down? Let's first predict it. Should the entropy be going up or should the entropy be go down. Entropy is going down. Entropy is going down because we're going from gas, 3 moles of gas to 1 mole of gas and 2 moles of liquid water. 2 moles of liquid water is going to be much more ordered. In fact, water is kind of unusually well-ordered liquid. And so entropy is going down. Is that good? No, because we want entropy to go up, but it must not have been too bad because this is what we call spontaneous reactions. So let's go ahead and calculate the entropy. Now, it's the entropy of the products minus entropy of the reactants. And so let's go back to CO2. ABC. So this is alphabetical order according to the base element. So we're going to go back to carbon here. So if we go CO2, we go out to the entropy, which is the third one. Entropy of CO2 gas is 213.7. Does that seem about right for gas? Yeah. But the units, be careful with the units because this is going to be 1 mole of CO2 gas comes 213.7 joules per mole Kelvin. So the moles cancel and leaves the joules per Kelvin. And then H2O liquid, we have 2 moles of H2O liquid. And so what's the entropy of H2O liquid? It was like 60 something. So let's go back to H2O here. H2O liquid was 69.91, kind of low. 69.91 joules per mole Kelvin. Moles cancel and leaves them with joules per Kelvin, and double that. Okay, minus the entropy of the products. Now, the entropy of the products would be entropy of methane gas. So let's go back over here and look at methane gas. Okay, so methane gas, we go over here. That's 186.3. It's kind of what we expect. It's a little lower, but 186.3 joules per Kelvin. And how about the entropy of O2 gas? Is the entropy of O2 gas 0? O2 gas? No. O2 gas is not 0. The enthalpy of formation of O2 gas is 0, but not the entropy. And so let's go back to O2 gas and see what it is. So we go back to O2 gas. Enthalpy of formation is 0. However, the entropy is 205.1. Is that what we expect for entropy? For gas? Yeah. Over 200, so 205.1. This is a little bit lower, but not much. So joules per Kelvin. And we have 202, so I have to multiply this by 2. So it's 2 times 205.1. Because if we have twice as many moles, we're going to have twice as much entropy, joules per Kelvin. And so what is the entropy change here? Entropy change, let's go ahead and calculate it. It's 2 times 69.91 equals plus 213.7. That. Okay, minus 186.3. What did you get?
-5.2.
Negative 5.2? Is that what other people got? Maybe it. This is going to be 400, 600, so it's minus 600. This is about 200 plus, about 200, 400 minus 600, roughly. And so it should be coming out a bigger number, 242.9.
Where did you get the 69.91 for H2O?
Yeah, H2O liquid. 69.91. We're allowed 1 decimal place, it looks like, or is that what people got? And so the entropy actually went down, the energy went down, so this is one of those question marks, but it looks like the energy won because this reaction goes, combustion of methane is spontaneous. And so now we can calculate it, but we have no way, how do we compare these two numbers? Because, the units are different. For example, for energy, it's the units of kilojoules. For entropy, it's the units of joules per Kelvin. And so how do we figure out how to compare these two numbers? So those are what we're going to talk about next for this. So I'll stop here.